Here is our fourth VODcast for graphing motion. That's chapter 2 of your AP Physics book. We're going to look at a position time graph and answer some questions. Question A says, find the distance traveled between 0 and 2 seconds. If we look on the x-axis, or on the horizontal axis, we see time in seconds. Here's 1 second, 2 seconds. And we can see that this object has remained at a distance of 5 meters, and its position has not changed. Therefore, the distance that it's traveled is 0 meters. Let's try question B. Find the velocity between 9 and 15 seconds. Well, here's 10 seconds. 9 is right there. 15 is here. Now, I'd like you to notice that the slope of this line represents the velocity, and it would actually be simpler to start back at 8 seconds and realize that the slope is the same for this entire interval. If we start then back at 8 seconds, we've got a rise of 1, 2, 3, 4, 5, 6, 7, 8, actually negative 8 meters over a period of 1, 2, 3, 4, 5, 6, 7 seconds. So that velocity equals slope. It's literally change in position over change in time, or negative 8 over 7 meters per second. Find the velocity between 5 and 8 seconds. Again, I'm looking at slope, and between 5 and 8 seconds, it looks as though my slope is 0. So my velocity is 0 meters per second. Finally, question D, find the average velocity for the entire interval between 0 and 15 seconds. To find average velocity, I only need to look at the initial and final position and time. So I start at 5 meters at 0 seconds, and then over 15 seconds, I travel to 0 meters. So my slope here is negative 5 meters over 15 seconds, or if I reduce that, negative 1/3 meters per second. Let's try another one. Here we've got a velocity time graph. For a velocity time graph, it's a little bit different. The displacement or distance traveled with direction is going to be area, and the slope is going to be our acceleration. Find the distance traveled between 0 and 3 seconds. So here's 0, 1, 2, 3 seconds. The distance traveled, again, will be this area. This object is traveling at 4 meters per second for a period of 3 seconds. 4 meters per second times 3 seconds is equal to 12 meters. It's positive 12 meters because it's above the x-axis. And you'll notice if you actually look at the area, you actually have 12 squares there, where each square represents 1 meter per second. Question B, find the acceleration between 3 and 6 seconds. Well, acceleration is slope, and I can see here that slope is 3 over 3, 3 meters per second over 3 seconds, or 1 meter per second squared. So our slope is our acceleration. And again, our area was displacement. And this is a velocity versus time graph. When does the maximum speed occur? I'm going to look at the graph again, look at the vertical axis for velocity, and notice that the maximum speed is here at 5, 6, 7 meters per second. Between when? Looks like it's between 6 and 11 seconds. Finally, find the distance traveled for the, find the distance traveled between 3 and 6 seconds. So the distance traveled is going to be the area of this trapezoid. And the area of a trapezoid is equal to 1/2 B1 plus B2 times the height. And you'll notice something interesting here, that this displacement is equal to 1/2 initial velocity plus final velocity times time. and those things correspond. My initial velocity is the height of my first base. That's 4 meters per second. My final velocity is the height of my second base. That's 7 meters per second. And the time that this occurs is 3 seconds. So 1/2 times 11 times 3. Let's see, that's 5 times 5 times 3. That's 16.5 meters. That's the area of that trapezoid. And it's also the distance traveled between 3 and 6 seconds. Okay, finally, we've got convert the distance time graph to a velocity time graph. So what I'm going to do here is determine my velocity for each interval. When the slope is 0 on a distance time graph, or a position time graph would be a better, more precise term. When the slope is 0, the velocity is 0. Here my slope is 1. Here my slope is 0. Here my slope was -8/7. What I'm going to do is graph this. I'm going to change my scale to make this a little bit easier to work with. I'm going to call this +1, and again, this is a velocity time graph. Call this -1. This axis is time. I'm going to keep the axis the same, which means that I'm going to look at these same intervals. So from 0 to 2 seconds, we have a slope and a velocity of 0. From 2 to 5 seconds, that's this interval, we have a slope of 1. From, where are we here? From 5 to 8 seconds, again, we have a slope of 0. And then from, for the rest, we have a slope of -8/7, which is a little bit beyond -1, and our graph would stop right there. This is a discontinuous function, so there are no connecting lines between those horizontal lines. Let's take a look at this exercise. We've got a velocity time graph, and I'd like you to go backwards and create a distance time graph. This is the same graph that we were working with before. We knew that this was 12, this was 16.5. At this point, you should be able to figure out the area of the rest of it in intervals. So here we've got, let's see, 1, 2, 3, 4, 5 seconds, and a speed of 7 meters per second, so this is 35. And then this final triangle is 1, 2, times 7 times 1/2, so that's 7 meters. So here's what I figured out. Make a T-chart. Time and position. Excuse me. Now I'm going to have to assume that at 0 seconds, I have a position of 0. After 12 seconds, I have a position of, after 3 seconds, I have a position of 12 meters. Then what happens between 3 and 6 seconds is that this thing accelerates, and its final position ends up being 28.5 meters. From 6 to 11 seconds, we go an additional 35 meters. So if I add, now I'm at 63.5 meters. And in the last 7 seconds, so that, in the last 2 seconds, that takes me up to 13 seconds. I go an additional 7 meters. That takes me to 70.5 meters. So I'm really going to have to change my scale up here. 10, 20, 30, 40, 50, 60, 70. I'm going to start at 0, 0. After 3 seconds, I've gone to 12 meters. And that's going to be a straight line. And the reason it's going to be a straight line is because my velocity here is constant. What I'm going to do next is I'm going to look at the next interval, which has an acceleration and ends up at 28.5. So this is going to be a curved line to indicate acceleration. For my next interval, it's going to be a straight line going up to 63.5. And for my last interval, it's going to be a slowing down. It's going to go up to 70. And it would curve. I should exaggerate these. If I could blow this up, it would be more curving upward. And here where the graph is indicating a slowing down, it would be curving downward. Okay, let's finish up with some sample problems with falling objects. We're going to use the same four kinematic equations, but we're going to use some assumptions, and the biggest assumption is going to be that the acceleration of gravity is negative 10 meters per second. Here's practice problem number 1. A rock is dropped off of a bridge into a river. The rock falls a total of 180 meters before hitting the water. How long was the rock in the air? Here we've got displacement. Now, previously we said that displacement was delta x, and that's still true. However, you'll sometimes see it written as delta y when we are talking about vertical information. And I'm calling it negative 180 meters because the rock is ending up below where it started. I'd like to know how long the rock is in the air. I know that the initial velocity of a falling object is 0. And I also know that the acceleration of the rock is negative 10 meters per second. So there is one formula that I can use from my four kinematics. I'll write it out, and I'll plug in what I know. The VI delta t term is 0 because VI is 0. Basically, what I have here is negative 180 equals negative 5t squared. So I have to take 180 divided by 5, that's 36, and then I have to take the square root. So t is 6 seconds. You do need to be able to solve these italicized problems with mental math. There is a portion of the AP exam that does not allow you to use a calculator. Let's try question 2. Use the rock in question 1. How fast will the rock be going right before it hits the water? Here we want VF. Now there are several different formulas you can use, but the one that comes to my mind first is this one. And all I have to do here is take the acceleration of gravity, which is negative 10, times the time in the air, which is 6, and I get the final velocity of the rock is negative 60 meters per second. Let's try question 3. Sue throws a ball straight up at 5 meters per second. If she catches the ball at the same height at which she threw it, how long will the ball be in the air? So we know the initial velocity of the ball is 5 meters per second, and that's up. We can make some assumptions here. One way to solve this is to assume that the path of the ball is symmetric. And that would mean that if the ball was thrown up at 5 meters per second, it's going to land in her hands at the same speed in the opposite direction, which is negative 5 meters per second. The acceleration is still negative 10 meters per second squared, and we'd like to know delta t. So VF equals VI plus A delta t. Negative 5 equals 5 plus negative 10t. Subtract 5 from both sides. Got negative 10 equals negative 10t. T is 1 second. Use the information in problem 3. How high will the ball go? We can make an assumption here too. At the maximum height, the time is half. So if the ball is in the air for a total of 1 second, the time that I'm going to use to find the maximum height is half a second. I still have an acceleration of negative 10 meters per second, and I still have an initial velocity of 5 meters per second. Oops, that's negative 10 meters per second squared. And what I'd like is I'd like delta y. I'd like to know the displacement of the ball. So again, I get out one of my trusty formulas. And I'll plug in the variables that I have. Let's see, 5 times 0.5 plus 1/2 times negative 10 times 0.5 squared. So 5 times 0.5 is 2.5. 0.5 squared is 0.25. And then this is negative 5, so a quarter of negative 5 is negative 1.25. So the answer is 1.25 meters high. Pardon me. Question 5. Jason hits a volleyball so that it moves with an initial velocity of 6 meters per second straight upward. If the volleyball starts from 2 meters above the floor, how long will it be in the air before it strikes the floor? This is very similar to what we did before, but we're going to use a calculator to solve it. It's not italicized, so you can use a calculator. We've got an initial velocity of 6 meters per second. If it's going to hit the floor, in this case, what we have for our delta y value is we have negative 2 meters, because we're assuming that the ball is actually going to end up below where it starts. Our acceleration, when we're using a calculator, we're going to use negative 9.81. That's the more precise value. 10 is what we rounded to when we don't use a calculator. And what I'd like here is delta t. You can see that we're going to use the same formula that we used in question 4. So I'm going to write negative 2 equals 6 delta t plus 1/2 times negative 9.81 times t squared. Now this is a quadratic formula, and you do need to solve it using either the quadratic formula or using graphing techniques for math class. And I'm going to leave it to you to solve this problem, but again, you do need to use the quadratic formula. So if you don't know how to do that, now would be a good time to look that up. For question 6, use the information in question 5. How fast will the ball be going right before it hits the ground? After we solve this, we would have delta t, and we would be able to use Vf equals Vi plus a delta t, and we would be able to solve for Vf.